Thanks everybody for coming. I really appreciate you guys taking the time out to listen to me. I'm going to basically try to follow on from the whole idea of Bohm-Pribram, which has gone down through Freeman neurodynamics, and Yeshua has done a great job of making sure to present a lot of the that sort of thing to everyone in his teaching series. And so I wanted to go forward here on what exactly I'm trying to accomplish and talk about some of the assumptions. So the idea is that in the holonomic brain model, you have the idea of the brain as a hologram. And so there are some questions that, that come to pass that it's like, how's this accomplished? What is it? How does it work specifically? And instead of just kind of, in a more general sense, how are the mechanics specifically encoding data, and how would that be working in the brain? And that's sort of been an area that is problematic for all of the models that are exploring, the way the brain works. So starting out, we're going to make some assumptions here that so the research into large and small scale synchronizations in the brain indicate a level of electromagnetic based modulation of action potential. So basically what we're saying here is that the brain, we're going to make some assumptions so that I don't have to go back over some things, because I do want to do just a little bit of review on a couple of different topics that I want everyone to focus on to try to suss out these mechanics that I'm talking about. So we're going to assume, without a tremendous amount of going back and explaining it, that electromagnetism is modulating action potential. We're going to be assume that the signals we've detected at the scalp are evidence for large-scale synchronizations, which play a driving role in large-scale features of brain function, but cannot capture some of the smaller-scale events of synchronization as found in dendrites, which Pribram favored as the locale of the most detailed information and differentiation. So that is something that has kind of been a limitation, because you'd have to get into very small scale recording, and that's very difficult with a live brain. And some of that's been done, but there's still, of course, a lot of work going there. But we're going to assume that that these things are occurring if they're happening at the large scale, that there is some level of it happening at the small scale. I do have a bunch of papers that I have in the references below that go into the fact that is actually occurring. And then this electromagnetic system works in conjunction with the accepted neural network mechanics, much like the rest of computer hardware and software systems play an irreplaceable role in the management and production of artificial neural networks. In other words, a neural network can't work without the rest of the computer. There's other things going in and making the neural network work. It's not just doing it on its own. So you need that sort of, system around, why are the cells connecting, how are they, what's directing them, and things of that nature. So you have to have the same sort of answers. You have to be able to, describe the equipment. So thus we have that a phaptic coupling is that is not mediated through shared ion concentrations alone, is of greatest interest to the advancement of the Freeman program in neuroscience. So, we have a phaptic coupling that is occurring through ion concentrations, that are through gap junctions, et cetera. But this is specifically, we're talking about the electromagnetic effects. We're talking about right-hand rule, induction, and things of that nature. And I'm going to try to get into some of the details of that, specifically with dendrites. But I'm going to say I do believe that this is happening in the larger scale features of neurons as well. It's just there. It's particularly interesting in the dendrites, so I'm trying to stay there, and that's where most of the papers that I have cited in the references below are going to stay in that, with dendrites, etc. So then also we're going to be assuming the dendrites have been proven to also have action potentials, which can be subject to the same EM mediated phaptic coupling. So the thing here that I've kind of hinted at, and I'm going to do this sort of in a tell them what you're going to tell them, and then tell them what you told them. I try to always do things in that manner. But for just a moment here, we'll just say, so what exactly am I talking about when I say that it is that the dendrites are fringes? We're going to get into a little bit of that with just some review stuff, because this is a multidisciplinary audience. And so, you'll have to excuse me if I go over things that all too well. Hopefully I won't bore you. But let me go ahead and continue to my next slide here. So here I'm going to talk about how this kind of like from a miles out view, some of the things that are connected to what I've been talking to you guys for a lot of years now. There are a variety. Oh, am I not sharing my? You know what? I'm not sharing. Okay, it's not sharing. Let's try this. Let me hit this. Okay. Did that work?
Yes.
Ah, good. Okay. All right. So I'm going to talk about a few of the things here that over the years I've related some of the ideas in physics, and most recently I posted that really long post on quite a few things, and so I'm going to try to speak very broadly about how this relates really quickly right here, just kind of hint at it, because I do want to get I want to keep it brief as possible. So we're going to be basically assuming that the brain is a holographic data system, and so it's holographic systems work based upon wave interference resulting in patterns of fringes encoded on a surface. In the cases of a typical hologram, that's a 2D surface. Well, it's not perfectly 2D, and I'll get into that. But the point is that it is predominantly 2D, whereas what we're talking about is going to be fringes that are in 3 dimensions, as the dendrites themselves being the fringes. So these fringe patterns alter wave reflection and therefore the shape of the incident signals that are reflected off of them. Then some of the things that are just kind of, once again, this is a million miles out, just starting with some topics that are of interest that we've talked about over time. So the interference patterns in different spaces. So one of the things I wanted to bring out, and I will be covering this again just a little bit later, is that superposed waveforms in 2D can be treated by Fourier analysis. So what I'm saying here is basically that whenever you're looking at just a typical set of waves that you're wanting to break them down, that is a little bit different than what we are looking at with 3-dimensional waves that have all these varieties of different angles of incidence that are in a hologram. And so that's where Gabor had stepped in and kind of advanced Fourier. So then what is interesting here is that, perhaps the implication here is that there is some sort of dimensional interchange that Gabor is reaching for. And so I wanted to kind of point out that, and this is once again kind of assuming that you know a lot already about holograms, and I'm going to revisit that in just a moment, so you'll have to excuse me if I'm putting the cart before the horse. Basically, fringes are encoded on a holographic plate. They're not truly 2D, but they're actually kind of like, and I just want to kind of call upon something here, kind of like compactified dimensions of the Calabi-Yau manifolds. Now, this is just, in reference to some of the interesting physics that may be happening in space as well when you're talking about holographic theory in space instead of just in the brain. And basically what I want to point out is that the actual fringes on a holographic surface are 3 dimensions. They are, small hills that are causing light to, be reflected off at different angles. So it's not actually 2D. There are holograms where it acts as a diffraction grating as the light passes through it instead of reflecting off of it. And so that is a little more like 2D, but either way, my point here is that there is a kind of a smaller 3-dimensional way of representing a larger 3-dimension, and so there's an interesting idea of dimensions there that is I just kind of wanted to hint at and maybe talk about in conversations long after this one. So, but basically, this to sum this up, there is an additional degree of freedom to encode the fringes if the dendrites themselves are fringes for a hologram. So that is the geometry of the physical neuron and dendrite shape is what I'm saying here. So now let's get into how that is occurring and kind of do a little bit of the recap on things. All right, so holographic encoding. So the necessities of timing and angles of incidence for the exact shape of fringe patterns. So this is kind of just a what I'm going to be going over here in the rest of the presentation, and so I don't know that it's necessary to go over this a tremendous amount right here and now, but just basically I'm going to be going over how it is that there are these necessities of the timing and angles of incidence that are not really thought about a whole lot whenever you're thinking in terms of signal analysis, which is a lot of what we do now, looking at brain waves and things of that nature. We're not thinking about the three-dimensional aspects of it. We're thinking more about the phase relationships and things of that nature. So then also there is this interesting idea of interference versus superposition that I'm wanting to use that terminology, though interference and superposition are typically kind of thought of the same. There is the non-destructive aspect of waves, sharing the same space in a medium. That is an important thing that I wanted to call out, and I want you to be thinking about as we're discussing this, and that is that the interference pattern that you see when waves are on a screen, when you're the peak to trough, they're matched up and you're not really seeing the wave. Well, the energy of the wave is still there in a physical medium. And that's why I want to talk about specifically mechanical waves, because the waves actually travel through each other. They don't bounce off of each other. So thinking in terms of physical waves is going to be something I want to try to get everyone to go with me on for a little bit, just to think about these facts of, that their energy is still there in a medium, specifically when there is a destructive interference in the air. In other words, in the medium, without it actually impacting some sort of detection surface. However, once it impacts the detection surface, it's going to be transferring the energy, and therefore that's where you get the places where the energy is canceled out versus transmitted, because that's actually what we're seeing in these fringes in the darkness and lightness. So that's once again kind of hinting at what we're going to talk about here. Then ephaptic coupling. In my paper that I wrote back in 2015, because this is kind of a continuation on that, or sort of an explanation of that. I actually use some of the same analogies, etc. It is a read and write as one operation sort of thing. And that is the reading of the substrate. The process of reading is actually also playing a part in the process of writing. And that's something that that I want to talk about in the way in which natural data systems occur. So that is going to be another thing that I want to address. So there is a duality of, duality of digital. Yeah, and then then finally looking at, there is what we're talking about here is that we know that there is an interesting aspect of the ability for connections between synapses to be encoding information because of the way that we are able to use them with modern computer neural networks. So there is the network aspect of it, and I'm going to be calling that digital. It's not, I don't know that digital is really the right word, but because there is an aspect of it that is discrete. In other words, I guess that's the problem I have here is that it's not digital, but it is at least discrete, and versus the analog aspect of it. And so what we're proposing here in this presentation is that there are complementary systems of discrete, which is your typical neuron doctrine with the synapses and the long-term potentiation and things of that nature. And then there's the analog aspect of it, which is the transmission of waves and their impact on the action potentials. And then finally, now that leads to symbolic representation. So that's going to be really where the kind of the heart of the matter is. I want to talk about how all the mechanics lead down to symbolic representation, because that's the that's the whole thing here. We're talking about how do we get to represent items in the brain, that are outside, just like in a computer, and talking about the idea of a key. This is something I've brought up numerous times, but basically the idea is that when you've got, 8 bits and a possibility of 256 numbers there, then what we used initially was the ASCII code, and we said, oh, that's an 8, okay, and I look it up in my little thing over here, and it says, oh, that's a little smiley face or something. I forget what it actually is in actual ASCII code, but it may be a H or something. But the point is that's an arbitrarily defined key. And what I want to point out is that there's nobody to arbitrarily define a key for the brain. In other words, the way in which it represents data has to be somehow defined by natural systems. So the transform from what is represented and how it is represented, the representation and what it's representing, that connection has to be something natural. It has to be something with mechanics. It has to be something in nature itself for that to for it to have emerged in any way naturally. So the point I'm going to make is that the symmetry imposed by the key, and that is basically whenever you have transforming structures, like light through a crystal. And I'm going to show this later with something that I've brought up a number of times, which is a phase conjugate mirror. And that is that if you've got a complex crystal, the light going through it in one direction, if you just reverse it, it will undo the changes to the incidence of the light and all the different angles that it gained by going through when it started out coherent, and then it starts going off in all these directions. If it's reversed from there, then it will actually come back together. And so there is a symmetry in the fact that it can go backwards through this crystal, and so therefore it is a way in which symbolic representation can happen because of that symmetry of the two-way path. There is the mechanics of the system itself can actually create the connection between what is represented and the representation. So let's go forward from here. So let's go to a kind of a quick refresher on holography. Some of the topics I've been talking about here. I love this little video down here in the left-hand corner by Q Day. What you're seeing there actually is it's not actually the video is not reversing. You look at a millisecond time there. It is what he's doing. He's got it gives off waves from the little pins that are the Eiffel Tower, and then there is a kick he gives the system, and that causes part of the wave energy to reverse and go back inwards and recreate the Eiffel Tower. And you see on the right hand side there, that's what's occurring. And some of the waves are continuing to go outwards, and then some start coming inwards after the kick. And so that is an interesting that was basically the solution to a certain problem in the development of these pilot wave walkers, and how it is that they can have a feedback system for the waves. And so that was this kick idea that he showed here is actually a great solution. But it's also about this idea of reversibility I'm going to be revisiting repeatedly. Then up in the top here, you just have that's just what a surface looks like that has fringes on it from a hologram when you look at it in very close range. This hologram here, that is the first hologram made by Gabor. I don't know if it's the very first. I think it was the very first, but it was actually part of his Nobel lecture. And then I just have the idea of here that you've got the superposition of waves, of course, leads to constructive and destructive interference. So now, like I said, this is going to be somewhat rudimentary, but I want everyone thinking in terms of mechanical waves. And so please excuse me for going back over these subjects. But it's important to note that what's occurring in a wave, so you have a longitudinal wave on the left, transverse wave on the top right, and then you've got some relay surface waves and things of that nature down here below to show some of the more complex versions and what is happening to the particles of the medium. And in the case of each of these waves. And of course, the important part here is the waves are a collective action. They're a collective action of the medium as it's, perturbed in some way. And basically what it is it's disturbance from equilibrium and its attempt through restorative forces to return to equilibrium, causing a lag time. And that's why waves propagate, is because of this lag time in the restorative forces. And so there is it goes both directions. So then let's talk a moment about the idea of interference, because that is going to be important and within the context of physical waves. So look at my time here. I just want to make sure I'm not going too slow, because I being verbose is kind of part of my problem. So I'm trying to keep it concise. All right. So constructive interference here, we've got here in the top left, we've got two waves. When they run into each other, they're going to be constructive for a moment. But then, of course, as they're out of phase, they become destructive. And so you can see this kind of behavior here. But what I also want to point out is how whenever we're looking at the two-slit experiment, what's occurring is that these waves are, it's the angle of incidence that is causing those fringes. As you see on the bottom left-hand side there, you see the light and dark. That is a function of the angle of incidence that it's causing it. So in other words, normally whenever we're thinking about signal analysis and things of that nature, whenever we're talking about brain waves or anything like that, a lot of times we're thinking, because of in the modern age we use frequency modulation, amplitude modulation. We use especially frequency modulation, in radio for all those years. And then we've kind of gotten on this kick of thinking in terms of those sorts of changes, whereas not really thinking in terms of the changes in angles of incidence and how those create these patterns of interference. And so that's what I want to point out here is even in your typical two-slit experiment, it is the angle of incidence that is important. And in here, over here on the right-hand side, you can just see, what it looks like, for two sources to be, they both are the same frequency, they're the same phase, and it's still creating these lines of destructive interference. So you can see like two of them in the top one, or 4 of them in the bottom one there. So that is something I want to focus upon, is this idea of angles of incidence. So it looks like I've already touched upon some of this, that it's not governed by timing alone. And then also the point with interference here is that there's two kinds of interference. So going back to the previous video, so you have interference actually occurring in the medium, but it's not really interfering, it's not really destructive in any way. The waves are able to pass right through each other without any changes to the waves. So even if the waves were head on from each other, the waves will continue afterwards, even though they will destructively interfere for a moment. It's not truly destructive, because there is what will happen is that in the medium itself, there'll be a rotation or some sort of stress that holds the energy of the wave so that the wave can continue after the destructive interference point. And that's an important point, is understanding that there is the ability for a wave to continue in a medium after it has destructive interference. When I talk about two kinds of permanent or temporary, once it is actually on a screen, then what you're having there is whether or not it's going to absorb, if it's going to be able to absorb the energy of the wave or not. And this is going to be happening in mechanical waves. In other words, this is the exact same thing will happen in mechanical waves that happens in electromagnetic waves. And that is it won't be able to transmit the energy unless it is a peak or a trough. That's the only way in which it's going to cause any kind of movement. Generally, it's speaking kinetically whenever you're talking about a mechanical wave in any surface that it's interacting with, and so you will have the same fringe pattern. But the thing is, it actually is kind of a little bit. What I want you to think of is collapse of the wave function. In other words, there is an actual sort of decision being made here at a surface. Upon impact with the surface, it is either transmitting energy, or it is not transmitting energy. So that is a kind of an important point that will come up a little bit later. So so again, the fringes are the angle of incidence combined with the transfer of energy. And so that is kind of an important part of the aspect of how it is that you end up creating fringes. And of course, once again, I've got this background here. You've got these wavy fringes, because that's actually when you look at a hologram at the surface level, it's got these little hillocks that make the fringes that are actually kind of carved into the substrate, or it's laid down. And the funny thing is, I've actually, just to kind of do an aside here, the modern manufacture of holograms is specifically that sort of three-dimensional feature, such that you can take a modern hologram and pour chocolate on it, and if you're very, very careful, when you take the hologram off of it, the chocolate will actually act as a hologram, because it has the same little hills and things. So it's a really neat little effect that it's just a very small set of features. So once again, important thing there is just to know that it's the angle of incidence combined with the transfer of energy, because that is going to be the key to holography, is the angles of incidence. So going back to angle of incidence equals angle of reflection. So you've got your regular, specular reflection, and you've got your irregular reflection based upon the, whether or not the surface is very uniform. Now, in a diffuse reflection, basically we don't generally know what the surface is like, and so it's going to seemingly be random. However, with a hologram, it is a very structured set of angles that the light bounces off at, and it is structured by the way in which the hologram itself is encoded. And so just, returning to some of the ideas of waves crossing through each other, turning inside out, like you can see here in the spoon effect. When you're looking into a spoon, the reason why your image is upside down is because of the fact that with it being a concave mirror, it's gone past the convergence point and basically turned the image inside out. And that's why you end up seeing the upside down image of yourself. And so there's that's what it talks about. It says image location here in the bottom right. That actually should be kind of the convergence location, but there is a question of what exactly is the idea of focus. Why is it that you need to focus? Well, you need to focus because light is coming into your eyes at a wide variety of angles of incidence, and you need to be able to resolve it down to a set of interesting angles of incidence. That's part of the whole way in which focus itself works. So let's go here. Now, this is just kind of some of the things I'm going to be talking about. I'm going to bring the slide up again, but just basically, I want everyone to be thinking about the idea that reversibility equals decoding. So, in the bottom here, this is actually one of my favorite images of phase conjugate mirrors. Phase conjugate mirrors basically reflect. They reflect back in the direction from which the light came. So the angle of incidence is directly, instead of angle of incidence equals angle of reflection, with a phase conjugate mirror, it bounces off and goes back exactly in the direction it came from. And so normally with a regular mirror, it would be doubly distorted as an image goes through, like a Coke bottle or something, and then comes back again, it would be distorted twice. However, because of the fact that you have a phase conjugate mirror on the other side, what happens is instead it actually undoes what it did. So there is this encoding and decoding as in the two passes. And this is with the word conjugate here, I've talked about cup and ball relationships, and I've talked about a number of things when trying to relay how it is that we can determine specifically the meaning of something. How does information itself actually exist? And in discussions that we've had, in the group. And so this is kind of relating back to that. So I'm going to continue forward. All right. So finally, one of the other things that we need is resonance, of course. So, we've got the bridge there that was torn apart by resonance. Eventually, I think it collapsed just from the wind. And over here on the right-hand side, that's just basically a wave pool in which there's a, whole number relationship for the frequency of the wave. And whereas what we see is a wave that looks like it's bouncing up and down in place, what is actually occurring is two waves traveling through each other and going back and forth between constructive and destructive interference. That's actually what occurs in these sorts of standing waves. So whenever we're thinking of resonance, we need to be thinking of the idea of constructive interference, often combined with reflection, where the phase relationship is key. So here's another diagram up in the top left here, going over the idea of resonance. So there is a timing that is part of how it is that we typically think of resonance, and that is adding energy to something at the right frequency allows you to increase the amplitude. So if it's at the resonant frequency, in other words, in the case of a metal bar, it would be like the middle point of it. You've got a certain length that would, if that's matching the actual size of the wave, then you're going to have a matchup between the wavelength and the physical size of something. That is kind of important, the physical size and the wavelength. But we're probably all used to seeing the idea of a somebody pushing somebody on a swing. Well, what's occurring there though is a little bit difficult for resonance because of the fact that each time that you're pushing at a little bit of a different frequency, but because there's both amplitude and frequency going on here. But that's just because it's not a perfect system. But the point is that when you add energy at the right time in a system that is waving, because basically what it's doing is it's displaced from its equilibrium, then it can gather more and more energy within that system that is storing energy. And so that's how you've got things like radio waves interacting with electrons and causing them to arise to a different level. And it's over here on the bottom left-hand corner. What we've got is two different tuning forks.
We don't see your slides.
Oh, really? Well, let me stop the share and try to restart it. I don't know why.
That's odd. I did see them.
Okay, let's try it again here. There. How about now?
Yep.
Okay. So in the bottom left-hand corner here, you've got these two tuning forks. And what they're showing is that the waves that are of the wrong frequency, when the tuning fork is longer, does not actually cause the other tuning fork to move. The waves just go right past it because it's not at the resonant frequency. And so it's not able to add just that little bit of energy required to disturb it slightly and then keep adding it over and over and over, because that's what a wave's doing, is it's hitting over and over and over and over. And then each time it hits, it's giving some of its kinetic energy to that that tuning fork on the other side there. And then eventually that grows as each one of the peaks and troughs continues to add to that to the energy that's being stored in the tuning fork. So there's just this interesting idea of how it is that waves are transferring energy over a distance that is important to the idea of how energy is transferred between systems, and specifically that are of the right frequency. Okay, and then just one more thing here in kind of reviewing some of the important topics is antennas are one of the things I wanted to point out here is you've got these different kinds of antennas. So once again, it's the same as the tuning fork. It's and it's a system that I'm going to point out that when we started encoding sound waves into radio, there's nobody who is deciding, well, this frequency means this. And this frequency means this. It was a system that used the natural way that things are. In other words, it used physics itself to encode the data of voices and things of that nature. We didn't go and make up some arbitrary, this symbol equals this thing like we do in computers. And it's because the information was waves, and so we were able to use the fact that it was already waves to just transfer it to another kind of waves. So in antennas, basically what you've got is as the electromagnetic signal goes across them, you're basically inducing currents, and then if it's of the right frequency, then you end up picking it up. And there's some interesting things I wanted to point out here on the right hand side, and that is this is called a Yagi antenna, where basically you directionalize your waves, and that's done by having the right sets of frequencies and set up in a way that you have constructive and destructive interference that creates these lobes that are a lot like you're familiar with in, like the lobes of electron orbitals, for instance. There is and so that basically makes it so that you're predominantly sending your waves in one direction. And that's what these Yagi directionalized antennas are for. So let's move forward here. So now one of the things I wanted to get onto is how a phonograph works. So once again, this was in creating a phonograph, there wasn't any kind of thought for a key for representing. There is just simply the encoding of data. So what ends up happening in your original phonograph is it's just a sound collecting horn that causes a needle to dig into and jiggle with the jiggles that in the air that you're creating by speaking. And then those jiggles are actually cut into the surface, and then all you need to do is then have either a needle that is not so sharp that it continues to dig into it, or just put it on there with less pressure. And what ends up happening is you can reverse the process. And so the initial phonograph is actually, and you'll see down there in the bottom left, that is what a record looks like. And there's two different ways in which you can record information in a record, and that is either having side-to-side jiggles or up and down jiggles, or of course the combination of the two. And those jiggles are going to translate, into sound waves. And that is, just a typical, it's an analog system for storing data. And so there's this idea of transmitters being able to pick up information and transmit it over a distance, basically using resonance to be able to transfer information, because information is actually being transferred, obviously, by radio waves. Information is being transferred by sound, and so this ability to transfer information is very important, because it also is encoding information here in these grooves in a record. There is an encoding of information that is critical to understand the idea of how a brain could encode information, and that, of course, as I'm saying, is via fringes. So going back to this, some of you may know that Bohm was also involved with Pribram, and they often call the holonomic brain model the Bohm and Pribram model of brain function, because the idea, one of the favorite experiments of David Bohm was this reversible laminar flow experiment in the bottom right-hand corner. And basically what it shows is that if you have a transform that is, if you have a transform that basically has some sort of symmetry, some way in which it's going to, you can reverse it. There are things in nature that we may have thought were not reversible that factually are reversible. And that's what we're seeing there. That's not that is a, forward only, though it does start over at the beginning, as a forward only video there. It is not reversed, by the video. He's actually physically reversing it, and you see the three drops come back into play. And so what I've got here is just trying to relate the idea of complex interactions being going through a medium, or going through some sort of intervening transformation, and then being reversed. And that is basically encoding, decoding, and things of that nature. So once again, just going back over the phase conjugate mirrors there, that I think is probably the very best idea of looking at how there would be, whenever we're talking about dendrites, for instance, that if we were talking about electromagnetic signals coming off of these wires in the brain, and we think of the dendrites as wires for a moment, then what you're going to have is it's going to have to pass through a variety of things. And whenever we're thinking about signals that have traveled through a lot of the brain, there's been these transformations that are transformed again, that are transformed again. But the question then is there a reflection back where there is the ability to transfer information from one part of the brain to the other, and the fact that the brain structure itself alters the angles of incidence, therefore the patterns of interference, in a way that that maintains a structure, and therefore maintains the information across these distances. That is going to be the kind of a key concept in moving forward and looking at this method of encoding data. So let me get another drink here, if you don't mind. What I have here on the left is it's actually an evolutionarily it's an evolved antenna. It was created by an algorithm, and for picking up specific ranges of frequencies and things of that nature. And it ends up doing much better than designed antennas. And NASA uses some of these evolutionarily created antennas. But the point here is that there is, when you have a way of altering a wave. In other words, if as something goes through this alteration process, like going through the crystal or going through the Coke bottle in the case of the phase conjugate mirror thing that I had in the previous slide, what can happen is that that creates another shape, a different shape, and that different shape can then be represented by, for instance, this antenna. So in other words, the fringe pattern that is created in three-dimensional space is going to be, instead of resonant on a typical antenna, whenever you're broadcasting, you're going to have this typical, long single wire that picks up signals based upon its length, just like the tuning fork does. However, whenever you've got a three-dimensionally complex signal, in other words, there are waves coming from different angles it's going to shape the way in which the interference pattern is created, and then whether or not it's going to resonate is going to be dependent upon weird shapes, like the antenna on the left and like the antennas on the right. And that, of course, is what I'm getting at here, is that that dendrites are acting like broadcast and receiving antenna to be able to communicate with each other. And why that's important is, of course, then now we need to get on to how it is that holography is valuable here. And I'm saying that they're fringes, but once again, we need sort of a mechanism. I do have this slide here. So there's some other ways in which you can create, like we've got a phased array here on the left that's actually creating waves that appear to be moving in the have an angle of incidence that is off from the original broadcast array because of the timing. That is an important aspect that I wanted to talk about here real quick, because it is going to be part of the dynamics. Let me see what my next slide here is, because I do need to get to how it is that it's creating a shape in three-dimensional space. Let me check my slides. Let's forward. Okay. All right. Once again, let me take a breath here, because I do need to get to something. All right. I'd like for you guys to imagine for a moment points at the surface of a pond, in 3 little points. If it's on the surface of a pond, I can create ripples at those points. And so long as I have them all, if I started all of them at the same time, they would all meet in the middle. And you'd actually see a larger lump in the middle than anywhere else in the area of this triangle of points that I'm creating ripples from, right? Just on a ripple pond. I can just create a single ripple and they'd all meet in the center so long as their timing was right. However, if the timing is different, so then it changes when each one of them emits a ripple, the location at which all three will have constructive interference will be altered to some other point inside that triangle. I hope that that's somewhat obvious without some slides that would require some creating some animations that I didn't have access to. But the idea here is that the timing of signals, once again, that I've been trying to get at, is going to change the points at which waves meet to create constructive or destructive interference. Now, in my paper, and this is where I'm going to just kind of chat for a little bit here, I point out that in gap junctions, we have ion concentrations that are that slowly change over time. So, well, between the astroglia, there are gap junctions that mediate slow transfer of ions, so your ion concentrations can change between the cells in the glia especially. And now this has already been part of aphactic coupling in the past, but I want to specifically talk about it instead of in terms of the ions directly having an impact on the action potential. Instead, what I want to talk about is the aspect of the shape that is created by the ionic concentrations as waves pass across them. So, as I said before, you've got these three different points at which, if I set off a wave, then it's going to have a little point in the center where they all constructively interfere. Now, if I had these be rods in space, and let's now make it sound instead. So long as the ping traveling up the rods, these three rods that are in a triangular shape, so long as they're all set off at the same time, then in the center there will be this constructive interference where the amplitude of the wave will be high in the dead center. But I can also alter that location simply by changing the timing at which those pings travel up the rod, and that will change the point at which the constructive interference, where it exists in it. And so I want you to imagine that point is creating basically a trace in the center as a signal is passing up it. And the same thing is happening whenever we're looking at the way a typical antenna works. There is, as the electricity passes up the antenna, it is not instantaneous. It actually is kind of like when you were a kid, you took a stick and ran it through water. You'd see these waves come off the location where you're running your hand through the water. The same thing sort of happens whenever you're putting energy into an antenna, and that it gives off one of those ripples. And then, of course, you do it repeatedly. You give off a repeated set of ripples. So thinking in those terms of displacement and giving off ripples, then as a signal is traveling down a neuron or down a dendrite, as an action potential is traveling down it, you are giving off these waves, and they are converging in space with other waves from other neurons, from other dendrites, anything that is activated in that area. And that's going to create, if it is a repeated process, it's happening all over and over. You have basically these antennas giving off waves. Then they're going to create a trace that actually can be stored by astroglia. So in other words, the ion concentrations are going to change in the astroglia to keep that trace in them. And one of the things that we found is now I need to thank Stuart Hammeroff for getting me interested more in the way in which microtubules work, because I ended up finding out a little bit more over the past couple of days than I had actually known before about microtubules, even though much of it was already sort of in my 2015 paper. So the process I initially mentioned in my earlier paper is that microtubules actually play a role in the way in which the dendrites and their spines actually form. In other words, the directions that they actually go. So how is it that, that's one of the things that they don't really talk about much whenever they're talking about the way that the brain works. It's like, oh, well, you have long-term potentiation. Well, what's that? Long-term potentiation is just a change in how much a synapse is reactive. So you just have more receptors and it's putting out more ligand and some combination of those two things. Well, how did these two things get together in the first place? Are we suggesting that all the synapses were already formed at the beginning when your brain as a child? Well, no, they weren't. Synapses continue to form and dendrites continue to change, and there's a tremendous amount of motility in the shape of the various cells of your brain, and during the formation of memories in an adult, and all throughout childhood, of course, especially. So, how is it? What is mediating these mechanics? What is making the direction? What guides a cell to grow in the correct direction? How does it know to reach out to the right place? It can't be magic. So we have to have a mechanism. We have to have something that is managing the creation of neural networks. So what is the system by which this creation of it, the actual formation, the guidance of the direction that it's going? And I'm suggesting it is specifically holography and these electromagnetic interactions. So going back to microtubules for just a moment, they're typically known. One of the ways that you'll most easily recognize them is during the process of mitosis, as you've got these are actual pictures over here on the left hand side, where the chromosomes are the blue and the green are the microtubules. And what occurs with the microtubules is they first have these spindles that form, and then they go to opposite sides and they kind of reach out and grow towards the chromosomes and then rip them apart. It actually, the actual mechanical part of it is on the chromosome itself, I believe, at the chromosome's end, and so it kind of more is pulling itself, I believe, but that's not important. The important part here is that the mechanics by which microtubules function is electromagnetism. They actually have been found to produce current. They align with magnetic fields. And this process of mitosis can be disrupted by strong magnetic fields. And so whenever you're looking into the properties of microtubules, you found that they are very, very much aligning with field lines. And so it is a very electromagnetic process. It's basically just like it's like a string of magnets just pulling stuff apart. It's very very mechanical and very directly and unambiguously based in electromagnetism. So the question then comes to, well, actually what I'm going to say is specifically that part of how these shapes of dendrites are occurring is through microtubule dynamics. And one of the things that we found in recent years, and again, I've got extensive references in the bottom here, that I would recommend looking into. They're all very good papers, but are very interesting anyway. One of the things that we're finding that's happening is that there's something called a tripartite synapse, where basically not only are dendrites and their spines reaching out, but astroglia are also reaching out, and there is organization of microtubules. So microtubules have generally been known as like the construction beams and things of that nature in cells. And one of the reasons why Stu Hameroff has he's been so connected to this idea of microtubules and consciousness is because whenever there's a variety of ways in which you can disrupt consciousness by disrupting microtubule function. In other words, of some of the different anesthetics disrupt the function of microtubules, and then that disrupts consciousness. And And so now, the one argument against that, typically would be, that instead of seeing it as some sort of quantum process, which I don't agree with Stuart on some of the leaps he's made in the way that it's doing any quantum processing. I instead see it as part of this formation of dendrites. But I'm sorry, I've kind of gone off to the side a little bit. Let me try to return back to where I was for a moment and look at it from there, because I've kind of lost my way. I want to focus specifically on the fact that they are exposed to electrical fields, magnetic fields, and that the gap junctions that allow these ion concentrations to change are then being organized and organizing the concentrations in the directions of the microtubules, which then determine the direction of the growth of these various aspects of the dendrites and their and the cells around them. So what I'm saying then is that the broadcast of the signals that are coming from these neurons that happen repeatedly are actually setting up a system where you have a way of creating short-term memory. And I believe, now this is a conjecture, that I believe short-term memory may be mediated by these temporary pathways of microtubules that go not just from the dendrites, but actually create these temporary pathways for field lines from what would normally be a synapse, and instead, like, it's an area that where you need a line from one area to another to represent a fringe. So going back to this, and I'm sorry if I'm kind of wandering around. This is a very difficult subject, but the whenever you've got these temporary lines that have been created, that are these three-dimensional shapes that are defined by the interaction of the waves that create the interference patterns, that create these fringes that are stored in the astroglia, then as ion concentrations, that then have these the gathering of the microtubules, which then align to it. And then what I'm saying is that not only is the pattern, the temporary pattern of the thoughts that you're having right now that are not long-term potentiated, they're not encoded, but instead they are temporarily created through these electromagnetic structures that are maintained through the ion concentrations, as well as the astroglia the microtubules in the astroglia aligning to allow a maintained field line. And so that is the basis for what I believe to be the way in which short-term memory allows a level of creativity that comes from the combination of these various waves that are created by our thoughts, which are these activations of these shaped signals, and then it's temporarily stored. And then over time, that, by the way, this is something I pointed out in my earlier paper, the growth of and the direction of the growth of the dendrites are determined by the microtubules. So what I was saying is the one way in which you could argue against Hameroff, that's what I lost, is that microtubules are also the structure on which all the various proteins and the various things that you need to create vesicles and stuff to release into the synapse, those are all ferried down microtubules. And so one of the arguments against the idea, so I just wanted to put that out there, is that, well, once you disrupt the microtubules, it can no longer ferry the different chemicals needed to the synapse. And so therefore, once again, you cannot, the synapse cannot continue to fire if it doesn't have support from the rest of the cell. And so that would be one way in which you could argue specifically against some of Hameroff's ideas. However, what I'm saying is, in a positive way, what we have here is a system that we didn't really have a description for before. We don't really have a way in which we say we get long-term potentiation. Great, but how did the brain organize in the first place? Why is the brain organization, meaningful? How are we storing information? What is how do we actually create some level of symbolic representation in the brain? Those things all have to be tied together into one singular system, and this allows us to tie it together into one singular system. So going to symbol creation for a moment. Now, this is something that we've talked about fairly extensively in the group, and I don't want to go on too far because, of course, my time, I wanted to keep it. How long we've been going? Yeah, almost an hour. So I wanted to try to cut it a little bit short and not talk too much about symbol creation, but I wanted to hit upon it lightly, and that is, some of the things that we found in the way in which the visual cortex actually picks up edges, for instance. The visual cortex actually physically represents, in other words, if you see the edge of something, out there in the world, the visual cortex is very directly translating from an edge on the, a line of neurons on your eye to a line of neurons in the back of your brain. Now that's the starting point, and there's many layers beyond that. But what you have to understand then, of course, is that the layers beyond that are part of pre-existing structures that already have encoded information in them. So some part of this, of course, requires that if you understand the human brain somewhat in computer-like terms, you have to have some mode for instincts. You have to have some way in which things like, why do we like the taste of sweet? Why is sex pleasurable? Why do we want to do anything? Something has to already have encoded information, some way in which to, recognize things, recognize wants, desires, and determine those things. So therefore, there's already some set of encoded information in the brain that is meaningful in one way or another, and so therefore there are already structures. And what I'm saying is that specifically there are large scale and small scale structures that have this information already encoded. So when we're talking about symbol creation, there's first you start with just the basics of, like, here's an edge, and you can see some of these. I've just pulled this from a paper that briefly kind of goes over it topically, and you can look that up later if you like. But there are these ways in which it first recognizes an edge, but then, of course, we're going to have to determine, is that edge part of a three-dimensional object? Is it, you're going to have to go from simple shapes to mild transforms, mild transforms, mild transforms. And so it's going to be transformed by the transform, by the transform, by the transform. As you're going through the brain, through these successive layers, the signal is going to have to be combined with other signals. And so it's the combination of these various structures. In other words, they're literally physical. They start out as physical structures that are directly, representative, and then become partially representative. And that is, of course, then in a holographic fashion, you're not going to be able to see it the same way that you would in a 2D fashion like this. In other words, whenever you're representing information in a hologram, and let's go back to that for just a moment. What you're actually seeing with a hologram is whenever you look at a hologram, that's laid down in front of you, you're actually getting information from every part of the hologram, and the angles of incidence make it such that light from one area might be additively or constructively interfering on your eye when you're at one point, and then the light from that same area, when you move slightly, will be destructively interfering with some of the other light. And it's only the combination of the light from all of the different places on the hologram that actually construct the picture on your eye through constructive and destructive interference. But it requires that there be destructive interference as well. So as all of the angles of incidence add up to the picture that you see, and that is the reason why you can get these different angles as you move your head around and you're looking at a hologram, is because of that combination of constructive and destructive patterns that are dependent upon the angles of incidence. And so, I talk, since like I said, since we could spend a lot of time talking about symbol creation, what I've discussed here is the kind of the start of the idea of how there is a direct correlation between the object and like a reflection. In other words, there is a physical ball and cap sort of relationship between what is represented and the representation, and because of that, and it's going through a transformative medium, and that is what's allowing you to have these symbols very directly real holographic physical representations. It's just we don't really recognize them as directly representative. And this actually happens in neural networks as well. Whenever you look at the data of for an image in a neural network, it doesn't look like any one of, like if it's a neural network that's encoding 0 through 9, when you look at the output from the area, it's not going to look like any part. You're not going to see parts of a 0 or a 9 or a 1 or any one of them. You see something else, and it's because it's so highly transformed with the other information. So I'm going to go just a little bit further here, and then we'll be done here, and we'll talk about this a little bit. I hope I haven't covered too much information, and if you've got questions and stuff, we'll go right back over it here in just a minute after I kill the other broadcast software. So some of the new conjectures here: the alignment and formation of microtubules in astrocytes may produce temporary electromagnetic reactive structures, so intermediary jumps between neurons, allowing short-term memory to be compared interferometrically with long-term structures, like much like what is done in dual exposure holographic interferometry. In other words, the permanent interference and energy transfer from waves into microtubules within astroglia. So the point here is that you can actually take two holograms, and you can have a hologram and expose it twice, and if there's any small changes to the object that you're actually creating the hologram from, you'll actually have this very fine differentiation that you can actually recognize in the hologram. So I believe that what our brain does is this sort of, we already have a hologram that is being created by the firing pattern of the neurons and their interference patterns. That's already being created by the structures that are already there. But then whenever we're having a conscious moment, we're actually comparing the various patterns of other information that's coming in. So we're actually creating multiple simultaneous holograms, and then looking at the interference of these multiple simultaneous holograms. Then finally, one of my other conjectures here is that if we have these structures that are actually that are creating waves that are converging, then we also have waves that are diverging as well. In other words, there's waves that are going out as well as the ones that are coming in towards each other, depending on where you're looking at it from. And one of the things that I've been looking at is the electromagnetic properties of neuromelanin. Specifically, melanin in general has special electromagnetic properties. One of the things we find is that in patients with Parkinson's, there's a problem with their neuromelanin, and I believe what that is evidence of crosstalk. In other words, what's happening is in the motor control areas of the brain, substantia nigra, you have highly melanized areas. So there's a tremendous amount of melanin there because I believe the structures are much more simple. It's a much more simple neural network where there is purposefully the blocking of the system that I've been talking about this entire time. I believe that system does not exist as strongly within the substantia nigra because of the fact that the neuromelanin actually is blocking these signals. But you also find that the neuromelanin actually is in there are small concentrations of it throughout the brain, and I believe that these may be creating chambers which actually separate some parts of the brain from other parts of the brain to make it so that in the places where crosstalk is valuable to create a particular picture, it is separated from where that crosstalk would actually be destructive. However, that knowing when it would be destructive and when it is not would probably be probabilistic. So I believe that the fact that it is not very concentrated, but is only it's in mild concentrations, it has to do with a kind of a probabilistic method of allowing the signal through these areas. So that is some of the new conjectures. And then some of the things I wanted to talk about briefly is just some of the, where can we go from here? Should we, because it's if this ends up being a workable model, then what else does it relate to? And of course, we've talked about this with holographic model of space, and some of the things that of course that are some of my favorite topics. But I believe that I've shown some of you the image up here in the top right, where basically what's occurring there is actually first the waves pass through each other, and there's actually part of the heart shape that is upside down, you'll see, and then it turns inside out and meets with other waves that are coming in, and that's when it creates the heart shape there. But this is printing on water. That's done by basically you see all those paddles around the edges. That's it's a way to create an interference pattern, and they use Bessel functions. But I believe that the combination of Gabor and Bessel will actually result in some better understanding of something that is not simply that 2D surface there, because of course what I'm talking about would be like many layers of this, because you're going to be looking at an interference pattern that is not just two-dimensional like this, but three-dimensional, in that it's going to be this large structure like a dendrite, like the shape of a dendrite specifically. So my final points are that I believe we've been two-phase focused. In other words, whereas it's been very valuable and useful to extend Pribram's research, we've been focused upon transforms. And transforms are for sussing out frequency relations, phase relations, but it disregards some of the geometric interference patterns as a source of data encoding. And so that is where I think where we've been, that's a valuable direction for us to go, and it's that research is absolutely going to help us get where we need to go. I believe that this is also something that because of the focus upon that, we lose the idea of this three-dimensional interaction and these interference patterns and how they cause a change in the energy transference patterns is basically what we're talking about here. System described as a combination of waveforms passing through brain matter, retaining superposition states, as well as energy transfer interference. So that once again, there are times when the waves will be passing through each other without actually giving their energy to any material. They'll continue to pass through the brain material to other locations, but then there are certain instances in which they will actually give their energy. In other words, the waves will give the energy to the physical material, and the reason why it does that is, of course, principles of resonance. But that is what's necessary for you to actually transfer energy is principles of resonance. So there are things like Froelich coherence and things of that nature that are, of course, of interest in this idea, and specifically what we find in transferring between biological molecules, especially in the brain, but particularly biological molecules, is at the terahertz range. We find that there is a tremendous amount of biological activity because of specifically the size and shape of the waves are matching the size and shape of your typical biological molecules, causing resonance and allowing them to, basically start to change a lot. And so that's a way in which the energy is actually being transferred. So there's just something to keep in mind, that there are these frequencies that are going to resonate with particular molecules, and that's going to be important in the way in which the energy is then transferred, and whether or not it's going to be a pattern that arises or it does not. So then finally, the final point here is the holographic Rosetta Stone. So in an analog data system, unlike human data systems where we have a key, it's not defined arbitrarily like ASCII, but instead relies upon wave mechanics. So in other words, there is a physical relationship, a real physical relationship. Though transformed, there's a real physical relationship between the things that you see and what your brain is physically making in these shapes. There is a shape, geometric. Though it is transformed, it is a geometric mirror, just like the phase conjugate mirror I was trying to show you there. There is because it is unwound, it's wound and then unwound. There's this encoding and decoding sort of situation that it happens because of the intervening mediums and the physics of that. That is the way in which symbolic representation encodes data. So, cup and ball relationship I've tried to point out, or mirroring is a term that I've used frequently. Let's see. The structure intervening alterations or transformations is what defines the connection between representation and what was represented. Then I just wanted to point out some of the other interesting things of the full neoclassical worldview, which actually all of these things that I've brought up fit completely within all of the other physics based things that are important to me. Though I've tried to stay away from those aspects of physics, other than trying to bring you to the mechanical wave intuition directly, and talking some about the stresses in a medium. All of these things do kind of connect to the worldview. Actually, they very specifically connect to the entire worldview. And so if you're wanting to go back over some of those things, there's the cells are sentient beings in the SBOC and BPM group. Specifically was one of the threads in which I actually hit upon a lot of these topics and how they interact with the full overarching worldview. And then from a more holistic overview, there's just my video that I did a presentation on, which was reverse engineering mysticism. So with that, I'm going to go ahead and kill my other stream. And let's see if if you guys would give me just a moment to check something out here. That's great. All right. And I'm going to end the broadcast there. That way, just to make sure.